Hello, everyone. Our ultimate goal is to look at the Schrödinger equation in 3 dimensions. And as our first step on the way there, I wanted to look at what do these derivatives look like in just 2 dimensions, and where we switch to polar coordinates. So the question I want to do in this video is say, okay, let's say we had something like this, where we're just looking at that, something like we'd have in the kinetic energy term of the Schrödinger equation, just in 2 dimensions. And let's say we want to switch to polar coordinates. So instead of x and y, we want r and theta. So because it's going to be a little bit of work just to even get this in the 2 dimensions, but it illustrates the techniques that we'll want to use when we want to go to 3 dimensions. So first, because I have a whiteboard and some markers, thick markers here, to save some space, I'm going to introduce a bit of new notation. And it's not a notation that I invented, but it's not a notation you'll see usually quite at this point in physics, but it's a nice compact way of writing things. So let me just introduce that first. Ultimately, what we want to do is we want to find all these derivatives. And so I'm just going to take a way of writing these derivatives where instead of writing this, I'm going to write this as just partial sub x. I'm going to indicate basically derivatives with subscripts. So when I write that, it just means the thing on the left. And if I'm actually taking the derivative of something, if I'm taking, for example, I have some function and I want to indicate the derivative of f with respect to x, I'm just going to write that as f sub x. So in general, I'm just going to use a lot of subscripts and everything, and that's going to make for a lot less writing, and hopefully I can fit a lot more into the whiteboard that way. So this is just notation. It's a notation that's used elsewhere in physics, so it's not a bad thing to get a hang of, and in my case, it's just going to save me a lot of writing, and so that's why I'm going to use it here. So what I want to do is, so in this notation, what I'm trying to find is what this looks like in polar coordinates. And so I can write out, sort of using the definition of derivative, how I get from one variable to another. I'm going to write out the long form first, and then I'll do the more compact notation, but just to make it absolutely clear. What I'm going to write is, like, for example, if I'm looking at df dx, I can write that as dr dx df dr plus theta dx df d theta. So that's sometimes one of the things that's called the chain rule in calculus, where if you're taking variables that are sort of depend on each other and you're trying to figure out the derivative with respect to one, you can kind of expand it out. You sort of go through, sort of basically sum over all these possibilities. Here I've just got r and theta. So those are my possibilities, but if I put those all together, I can write one derivative in terms of other derivatives. In the notation that I've introduced, how would we write this? I would write this as f x sub x equals r sub x f sub r plus theta sub x f sub theta. A little bit easier to write. And in fact, if I wanted to, I could even take the f sort of out of here, and I could write this as partial x is equal to partial r partial x. Write it like this in the long form. And again, in my short notation, this is just going to look like this. So a little bit less writing, hopefully a little more space on the whiteboard. So I want to use that to basically expand out what is this second derivative, this sum of second derivatives. So I've got part of it already right here. So I've got what I want kind of on the bottom. So I just need to take another derivative there. And so let me, to get that first term. So, and again, when I take the second derivative, I'm going to indicate that by just doing two subscripts here. So I'll just write it as that. And in my notation, that's equal to, I can take the derivative of this right-hand side with respect to x. That's what I want to do here. And now I just need to expand this out. So I've got two terms here, and like usual, I just need to write this as the sum of two things. So I'm going to act with the derivative with respect to x on r sub x, which is the derivative of r with respect to x. So I'm going to get a second derivative there. So this is equal to, I'm going to write this as rxx d sub r plus, or the derivative operator could act on the second bit, r of x, and then I'll have the derivative of whatever this thing is acting on. So if I'd left this as f, this would be df dr, and then I would take d by dx of that. I'm going to write that as partial x partial r. I'm going to need to expand out what that is, but I'm going to leave that, I'm going to write it that way for the moment. But I've got derivatives with respect to sort of different sets of coordinate systems, so I need to clean that up. But let me finish writing out the rest of this. I'll have theta xx partial theta plus theta x partial x theta. Now let me write out, so I've got these terms, this partial xr, partial x theta. Let me need to expand out what I mean by that. Well, what I meant by a derivative with respect to x in the first place is, remember, I unfortunately erased it, but we said this chain rule, the derivative with respect to x is really just rx dr plus theta x d theta. It's actually what we went into there in the first place, what we took the derivative of. This is what we called the chain rule just a moment ago. So I'm going to use that to expand out the dx's the derivatives with respect to x there. I'm going to leave this one as it is. But then in this term, I'm going to write this out this way. So I have rx partial r, and then that's acting on this partial r. So this is just the second derivative with respect to r. And then this acting on partial r, which is going to give me the second derivative, but with theta and then r. That's this term. And then this term doesn't change. I'll leave it like that. And then finally, this last term looks pretty similar to what we did here with the second term. I've got partial x acting on partial theta. So it's going to be rx dr theta plus theta x partial theta theta. All right. So this looks like quite a bit, but we're almost there actually, because we've left this very abstract. This is going to make it easier for us to kind of get somewhere and get to the end. Because what we can do here is, I haven't yet actually put in, I haven't said what r is as a function of theta or of x and y. I haven't put in what theta is as a function of x and y. I've left it completely generic. So that means if I wanted to do the same thing with the partial y term, remember that's what I ultimately want. I'm basically looking for this plus partial y, the second derivative with respect to y. Then so far, since I haven't plugged in what x and y actually are in terms of r and theta, I can just change the x's to y's, and this is still true, and then that works. So that's nice. And then all I have to do is just figure out what these actual, then I can go and plug in what is the derivative of r with respect to x, second derivative, what is it squared, and I can plug in what those things actually are. And that'll let me solve what I want to do. So first, let me just combine some terms. There's two terms I can combine. So it looks like 6 terms, really I've got 5. Because what I can say is that for well-behaved functions, and this is generally true in calculus, for well-behaved functions, it shouldn't matter what order I take the derivatives in. So partial r, partial theta should be the same as partial theta, partial r. So I can combine those two terms. In fact, they have the same coefficients. So that's easy. So in the end, what I have is this second derivative with respect to x is equal to, and I'm just going to write out the rest and then combine those two terms, rxx partial r plus rx squared partial rr. That's this. This term gets combined. I'll save that till the end. I'll save the combined term until the end. So I'm going to write this term theta xx partial theta plus theta x squared, this term partial theta theta, and then the terms that I'm going to combine are, there's 2 of them, so there's 2 rx theta x, and then this mixed derivative, partial theta partial r. So that's what it looks like for x. The same thing, I want to write the equivalent expression for y, it's exactly the same. I just replace all of the x's with y's. So I can write that out. Theta y partial theta plus 2r y theta y partial theta r. So I saved myself a little trouble there. Finally, what I want to do is I want to take these two and just add them together. This one and this one. Add these two together because that gives me what I want. And you can see that I can combine some terms. There's a lot of similarity here, so it's going to allow me to write that in a nice, in a somewhat simpler fashion. So, for example, I can combine terms with the same derivatives in them. So let me write that out, and I'm going to reorder it again just slightly, for convenience sake. I'm going to put the second derivative bit first. So I'm going to have, let me write it up here. What I'm finding, I have rx squared plus ry squared partial rr. Then I'll do the partial r term plus rxx plus ryy partial r. Then let's do the theta terms plus, and again I might as well, I can write them as similar. So I have a theta theta term, and then I'll do the single derivative with respect to theta. That again, it looks very similar to what was with r because I haven't plugged in what r and theta are as functions of x and y yet. So really no reason for these to look any different. And then finally the mixed term plus 2 rx. Well, now I have to put a parentheses in here. I have rx theta x plus ry theta y, and that's the mixed term, partial theta r. Okay. Believe it or not, we're getting quite close here because now all we have to do, clear this some space. Now all I have to do here is we're going to plug in. Okay, so what are these Rx and Rxx's and theta x and so on? We just need to plug those in and then find out that fortunately a bunch of stuff is going to cancel. and we'll get a much simpler looking expression at the end. But first, let's write out, let's see how I can do this on one whiteboard. First, let's write out, okay, what are r and theta? The nicest way we can get what these things are is to just write, for example, r squared is x squared plus y squared. And then what we can do is we can take the derivative of both sides of this equation with respect to x. So for example, if we do that, then we get 2r dr dx, which is, that's what that means, equals 2x. So I get that rx equals, 2's cancel, and I just get x equals r. And in fact, if you remember, in polar coordinates, x is just r cosine theta. So this is actually just cosine theta. I just want to write it in terms of r and theta. Similarly, you can kind of see that, x and y come into this expression for r in the same way. So r, the derivative of r with respect to y, is just going to be y over r, which is sine theta. Okay, so that's the first derivatives. Oh, right away I can simplify something because I've got this term here, rx squared plus ry squared. Well, cosine squared theta, that's going to be cosine squared theta plus sine squared theta. That's just equal to 1. Cosine squared plus sine squared is equal to 1. So I'm going to come right here. I'm going to come back, see if I can write this in. I'm just going to say this is just 1. So that's nice. What about second derivatives? I could do this in a number of different ways, but I could just say I've got the first derivative here. I could just take a second derivative of this one. So if I take the derivative with respect to x at both sides of this, I get that r xx equals, now I have to take the derivative with respect to x of cosine theta. Well, derivative of cosine theta is minus sine theta, and then I have to take the derivative of what's inside because I'm taking the derivative with respect to x, not theta, so I get theta x. I haven't figured out what theta x is yet, though, so maybe I'll leave that. Ryy is similarly cosine theta y. Well, okay, let's go figure out what theta x and theta y are. We're going to need those anyway. And again, this one's a little more complicated, but what we can write is we can write that in polar coordinates, the tangent of theta is y over x. And again, I can take the derivative of both sides, this time with respect to x and y, and rearrange what I get to solve for what I want. If I take the derivative with respect to x of tan theta, so what is the derivative of a tangent? You might not remember, it's 1 over cosine squared, or sometimes called secant squared, but I'm going to just call it 1 over cosine squared. I don't want to deal with those inverse functions. But I'm taking the derivative with respect to x, so I also have to get a d theta dx. So that when I take the derivative with respect to x of both sides of this equation, I get theta x over cosine squared theta. And then the derivative of the right-hand side with respect to x is, I've got x in the bottom there, so it's x to the minus 1. So I get minus y over x squared. And so let me rearrange this a bit. Theta x is minus y cosine squared theta over x squared. But here I can, now I want to write, I can substitute in, I can say x is just r cosine theta. That's what it is in polar coordinates. So I've got an x squared in the bottom here, so that's going to be r squared cosine squared theta. So the r squareds are going to cancel there. I'm sorry, the cosine squareds are going to cancel there. I'm going to have minus y over r squared. Y, though, is also just r over sine theta. So I'm going to write this as minus sine theta, almost ran out of room, over r. Just barely squeezed that in there. Okay. Um, theta y is actually probably a little easier because look at y is on top, but similarly, I'm going to have theta y over cosine squared, because I'm still taking derivative of that tangent there, equals derivative of the right-hand side with respect to y is just 1 over x. So here I have theta y equals cosine squared over x. And again, I can say, well, x is r cosine theta, so this is going to be cosine theta over r. So I think I'm running out of room a little bit here. Unfortunately, something's going to have to go. But let's see. Well, I already found out rx and ry. Yeah, I can't save it all. Well, first we can probably see what these are. So rxx here is minus sine theta times theta x. Theta x here was minus sine theta over r. So this is going to be equal to, I don't know if I can squeeze it in there, but I've got minus sine theta times minus sine theta, so it's going to be plus sine squared theta and then over r. But sine squared theta over r, kind of squeezed in there. Ryy is similarly going to be cosine. I've got a cosine and a cosine, and then over r, so it's really just cosine squared over r. All right, so that actually, now I can cross out rxx plus ryy then is sine squared theta plus cosine squared theta over r. So let me clean this up. So this was just 1. I'll just write. Well, I can just erase that. So I have that. And then this term is just 1 over r. Okay, we're making pretty good progress here. It's looking a lot simpler. Meanwhile, I can also do this mixed term here, actually, because I've got all the things I need here. In fact, I've got most of what I need except for those second derivatives with respect to theta. So let's see. I've got rx times theta x. So where is that? That is cosine theta is rx, and then theta x is minus sine theta over r. So I've got basically a minus sine times cosine over r. But then when I look at the ry theta y term, that's going to be sine times cosine, but there's no negative sign. So it's going to be sine cosine over r. The other one's minus sine cosine over r. So these two terms actually cancel. So this just goes away. This mixed derivative term, it is just 0. That is just 0. More progress. This is great. Theta x squared. I've actually got that squeezed in here. Theta x squared plus theta, I'm sorry, that's rxx. Where's theta x? Theta x is over here. Theta x squared is, the squared is going to get rid of the minus sign. It's just going to be sine squared theta over r squared, and theta y squared will just be cosine squared theta over r squared. So again, I'll have sine squared plus cosine squared over r squared. So that's sine squared plus cosine squared is just 1. This term just becomes 1 over r squared. Magical. Finally, almost there. We just need this final derivative of theta xx with respect to x. Theta y, we need to take the derivative of this with respect to y. Almost there. We can write that out pretty quick, but I do need some more space here. Let me see if I can actually squeeze it in up here. Because what do I need to do? I need to take the derivative of this with respect to x and the derivative of this with respect to y. So I need this. It has 2 terms. If I take the derivative of the top part, sine theta, then I get minus cosine theta times theta x over r is one term. And then I've also got the thing on the bottom, so that r to the minus 1, so that becomes minus the sine, leaving the sine theta alone, over r squared, and then I have derivative of r with respect to x. Okay, this is all theta xx. So, but I already know what theta x and rx are. I've calculated those. In fact, theta x is right there. So I've got a minus sign and a minus sign, so that becomes positive sine times cosine over r squared, because I've got factors of r. So I've got sine, cosine. I didn't write the thetas. You can figure out what I meant. And then I have rx, remember, was just cosine theta. So I have minus sine theta cosine theta over r squared. Minus sine cosine over r squared. Look at that. It's 0. Those two terms cancel. A similar thing we can see, maybe we can see, I don't know. Let's do it. Let's see what happens with the theta yy term, but we can probably guess that it's going to be similar. I feel like I forgot a minus sign there, but it looks okay. A minus sign, positive, minus sign. We'll check. I take the derivative of this with respect to y, I'll get here a minus sine theta over r, and then theta sub y. And then the second term is minus cosine theta over r squared, r sub y. And again, we know what this is. This is going to give me a minus sine cosine over r squared. This is going to give me a minus sine cosine over r squared. So that's actually minus 2 cosine. I think I messed up one of the signs here. These aren't supposed to cancel individually, but let's go back. This term should cancel this term. So I think I just fudged the sign over here somewhere. So let's go back and just make sure. So theta x, if I take the derivative with respect to x, get this had a minus sign to begin with. That was true. So if I take the derivative with respect to x, I get cosine theta x over r. Oh, yeah, so that gave us a positive term. That's what I did over there. And then I have the derivative of this one. Oh, I think I see where I went awry. When I take the derivative there, I'm getting a minus sign because the thing is negative to begin with, but then when I take the derivative of 1 over r, I get it becomes positive again. So I get that should be a positive term, actually. And then sine theta over rx, everything else I think was good. So yeah, this should be a plus sign. So individually, the terms are not 0, but one is plus 2 sine cosine over r squared. The other is minus 2 sine cosine over r squared. They cancel, and this term goes away. So you can see, it's a bit of bookkeeping, and even I practiced this before I made the video, and I still managed to make one little mistake there at the end. But it's a bit of work, but we finally did it. We found that this, what's called the Laplacian in 2 dimensions, this second derivative, dxx plus dyyy is just equal to this. And to sort of undo the compact notation, remember what this means. What does this mean? This means that the second derivative with respect to x squared plus the second derivative with respect to y squared, sorry, not squared, this is just a second derivative, equals second derivative with respect to r plus 1 over r d by dr plus 1 over r squared, second derivative with respect to theta. So that's what's called the Laplacian in polar coordinates in 2 dimensions. Ultimately, what we want to do is we want to do this in 3 dimensions with spherical coordinates, but it's not really any different. It just takes more pages. It takes longer. I don't know if I'm going to go through all of that completely, or just I think we'll just skip to the result and then actually look at sort of the physics. But you get sort of a similar thing where it's not completely trivial looking. Like I don't know if you could have guessed this. These factors of 1 over r and 1 over r squared, and the fact that things look a little weird, but a lot of interesting physics will pop out of that. But that will be the topic of another video. Thanks for watching.